Welcome back, everyone. We're here to talk about DC motors today. Really, our introduction to motors as a concept, period.
Yep.
So, we're going to be hitting that, kind of going through what a DC motor is and the basics of how it operates.
Yeah. And so we're going to talk a little bit about some motor anatomy generally, and
Yeah.
then we're really going to kind of focus in on like the mechanism by which like a motor spins, essentially. So, with that in mind, we will get started.
So, a motor is essentially a transducer of sorts.
Yeah.
In our broad systems perspective, it is changing an electrical power source to a mechanical power source.
Yeah. It's translating one form of energy into another.
Yeah.
So,
So we're turning electricity into a rotational mechanical
output,
energy.
or we're turning electricity into torque, essentially.
Yeah.
So,
Motors have there's just such a wide variety of them. We're going to scratch the surface here. Even within DC motors, there's so many different types.
and variants and optimizations that get made for different applications. So
Yeah.
like we're not going to this is not an exhaustive list on motors and all of their nuances and everything. This is like the operating principles by which they kind of all conform to.
Yes.
So most of the time when we're dealing with if we're dealing with any electric motor, your input is going to be electricity.
Yeah. And that's true. Like it's just the type of electricity that we're talking about as the input. Versus like a DC motor is going to take DC into it,
Yeah.
whereas an AC motor is going to take AC into it.
And they both translate those into
Rotary motion at the shaft.
Yeah.
So it's a speed and torque thing.
Yeah. And so there are a couple things that are going to generally here, like we're going to have some common features across like almost all motors in some capacity are going to have some variants of these types of things,
Yeah.
with the exception of brushes. Those are unique to DC motors.
Yes.
But a termination box, this is where you're going to basically have the power input to the motor.
So you're going to make the connections between your physical power coming out of the wall and the individual field elements that are inside of there.
Yeah. The brushes here, we're going to talk about these in more detail, but they make contact with something that's called the commutator, and it's responsible for essentially making the corresponding magnetic fields we need to make a motor spin. And we'll get into detail there in just a moment. But just understand, brushes and commutators go together. We're going to talk about them in more detail. And then we also have the armature. This is the
part that spins.
Yeah, this is oftentimes interchangeably called the rotor.
So it is the rotor. It's called an armature in a DC motor because a DC motor has windings in the center, and an induction AC motor does not.
Yeah, so like when we get to AC motors, you'll see how those function and all that type of stuff.
Yeah. And then you might have field windings, or it might be a permanent magnet on the outside.
And that again kind of depends on the type of motor you're dealing
And
with.
again, on DC motors, you can also have permanent magnets on the inside, depending on the geometry and format
Yeah,
of it.
it's so like just like at the end of the day, what we're looking to do is get some magnetic fields to interact with each other to turn this into rotational energy. So then there's often going to be a core associated if you have windings for your fields or you're on your armature. There's some type of core associated with it to kind of enhance that magnetic field that we're generating.
Yeah. So because iron is an extremely good conductor of magnetic fields.
Yeah.
We often use blocks and chunks of iron in order to shape that magnetic field.
And we see this again and again in a bunch of different applications, from transformers. It shows up in AC motors. It shows up all over the place. Like we use it a bunch. Other thing here, big thing. Not all motors have cooling fans per se, but most motors have some mechanism of dealing with some type of cooling, whether it's passive or active. Motors get
And since there's something that's rotating anyways, oftentimes they just put fan blades on the shaft.
Yeah, and it just makes it easier. Bearings and the shaft. Okay, so these are kind of some things that
They're just mechanical system components.
Yeah.
and they're passive as far as the mechanical advantage goes. The bearings reduce friction as it's rotating in there, and hold the load of the shaft in whatever direction, hold it steady.
They're basically responsible for locating the shaft in predictable space.
In predictable space and supporting it and while doing that, reducing friction.
Yeah.
The shaft itself, it's just a bar.
It's the actual output of the motor.
It's the actual output of the motor.
Yeah. You attach whatever mechanical system to the shaft, and that's how you translate. That's how this conversion of electricity into mechanical energy
Works,
gets.
yeah.
Okay.
So, in motor terminology, you have the stator and then you have the rotor.
Yeah.
The rotor is what's rotating. The stator
stator.
is what's standing still.
Yeah.
It gets confusing because in some configurations, the outside is the part that's rotating and the inside is what's staying still.
And this is something like when you start getting into like very small motors, they often flip this relationship versus big motors.
Yes.
But ultimately, at the end of the day, both of the rotor and the stator, they need to be generating some type of like magnetic fields that are going to interact with each other.
Yeah. So what you are doing is you're creating different magnetic fields. Like if they're different in their orientation of the magnetic field, like otherwise, like north and south attract, right?
Yeah, they will pull towards
so
each
they'll
other.
pull towards each other, and then in other polarities,
They will
they will repulse.
Repulse
And
or
so
repel.
this causes that, like the attraction to the next field and the
Repulsion.
repulsion from the last field are what's going to cause this rotational motion, and it's called the Lorentz force.
Yeah, and the reason we get to do this just at a very high level is that any time that we have current moving through any type of conductor, we are going to generate a corresponding magnetic field that's proportional to the amount of current that's flowing.
And we'll go into great depth in the panel build class about induction and what that is and how that works. In motors, in this class, we're basically taking that information and we're using that to generate rotational
Force.
force.
Yeah. That's what we care about in this circumstance.
That's what we care about in this circumstance. Yeah.
Video link here for like a visualization of how this process works. They're very good to watch. Highly recommend you guys watch this. It will do a better
They
job.
have great animations that I'm not capable of generating.
Yeah, and seeing this in action is much easier to understand how these things relate to each other than us talking about it at you. So watch this video, please. So when we're talking about the main thing for DC motors, though, is this concept of commutation and the commutator and how it relates to like how we're doing power input.
So remember when I was talking about different polarities repulsing or attracting, the thing is if we just had a motor and it was just hooked in DC and it just had current going in one direction through it, nothing would change. And so therefore it would just lock itself in the position that it's in and it would not rotate.
Yeah.
So we need to do something called commutation in order to alternate the current inside there. So in essence, like when we refer to a DC motor, we're just talking about what we're putting into it.
Yeah.
Because it is using this device right here, a brush and a commutator that basically alternates the polarity, flips it back and forth.
We're creating an alternating current inside of the motor.
And it's not a sine wave. It's not any of those things that you assume with alternating current. It's just like it's more of a pulse.
Yeah.
Like a pulse back and forth. But brushes are just basically graphite bars.
Yeah. And we dope them sometimes with aluminum or copper to enhance their conductivity.
Yeah, to enhance their conductivity. But essentially, they're just there to transfer electricity as something that is spinning. And so you'll notice the commutator is just made up, it's a circular array of contacts.
Yeah.
And each of those energizes a different field winding that you see carrying down the rotor on this diagram there to the right.
So like here, like if we're looking at like this patch of copper here, it is directly connected to a coil of wire, and 180 degrees from this patch on the opposite side of this commutator is another one that forms the connection to the other end of that coil.
Between positive and
The
ground.
negative. Yeah.
And then the next, like as it rotates then,
Yeah.
it's switching the next coil to the next coil to the next coil to energize that,
Yeah.
which allows that alternating to happen that causes the repulsion and attraction that
Yeah.
goes
So
from-
like essentially we have a bunch of field coils that we are going to energize kind of like in sequence, and their polarity is going to shift based on their relative positions to the two brushes that are there, because one brush is positively charged, the other one is negatively charged, and depending on which orientation it's in, we're getting we're getting different polarities out of the
and
fields.
relation to the stator fields, which
Yeah.
we will cover a little bit later. So
Yeah.
and here actually right
Yeah.
now, these are the sort of field windings on the stator portion of it. And so these form a constant, like stationary north and south pole that doesn't alternate
Yeah.
in most configurations.
Yeah. It's
And we'll get to that like later. You'll see a whole bunch of
There's-
different geometries
and
that
there's some edge cases where they do technically change, but like we'll address those when it's appropriate.
Yeah.
Like
But yeah, so these are what those rotor coils are, or armatures are interacting with.
yeah, and so like when we energize this motor, one side of this set of coils is going to become your north pole, the other side will become your south pole, and then the brushes are going to create essentially the opposite.
Yeah. So the brushes are generally like, if you take a look at these two windings here,
Yeah.
it's coming. The brushes are coming in between there, and so they're energizing coils that are in between the two of them. And so then when it energizes it, one side becomes the north pole, one side becomes the south pole. So it's automatically drawn
Exactly.
off center of that,
Yeah.
and then the next one is then made connection.
and it
And
does
it's
the
drawn
same
off
thing
center.
again.
And so it's through the series of those coils being
Yeah.
energized through the commutator, that's what pulls it around.
Yeah. So this comes into like the kind of the next like topic we kind of need to be aware of.
And we go into way more detail
Detail.
on EMF in the AC panel build
Yeah.
class, but this is an important thing to kind of relate to here. Because we are talking about conductors moving through a magnetic field, there is induction happening.
Yeah.
So during operation, voltage is induced on the armature wires in the opposite direction. This causes resistance, this back EMF.
Yeah.
And that's why it isn't a short circuit.
Yeah, and this is the thing that I think a lot of people struggle to wrap their head around the first time that we talk about this, because like you really have to have a solid understanding of how induction works fundamentally before we can really dive into like the effects back EMF like has like on a fundamentals level around why DC motors only spin so fast and how you can get only so much torque out of them. It comes back to
That back
The
EMF
EMF,
that comes into it. Yeah.
So
So it's important to note
Yeah.
you're going to experience more when we talk about induction in
Yeah.
the other class.
I think broad level here is like the faster a motor is spinning, the more back EMF you're going to experience.
And so it limits the upper end.
It limits your upper end in terms of both like how quickly you can spin, but also the maximum amount of torque you can apply.
Yeah.
So this is an explanation in a little bit more detailed.
And what we get is a torque speed curve, something like this, where essentially in a DC motor, it's important to realize that this is a linear thing.
Yeah.
We basically have this stall torque, so the maximum torque is at the low end of the rotational speed, and then at the maximum speed, we're going to have the least amount of torque.
Yeah, and so this is actually something that this is a characteristic of DC motors that can be quite useful for a lot of applications. But torque these torque curves that we're looking at here for DC motors, they're basically all linear. When it comes to different types of motors, you will see that these curves look very different.
Yeah.
So,
So let's take a look at this. So like it's proportional to the armature magnetic field strength, which is in turn due to the proportional current through the armature windings. And you know, like this is just some words that maybe you should kind of like absorb on your own time.
yeah,
But like what this yields is that speed, on the other hand, if we go to the next slide, is limited by that counter EMF, and that counter EMF is overcome by the voltage,
yeah,
right? So that means that like basically like the counter EMF is causing a voltage drop because it's essentially acting like a resistance.
Yeah,
Because going in the opposite direction, it is subtracting from the voltage that we're applying in the forward direction. And what this means is the more voltage we pour into that motor, the more speed we get out of it, because that back EMF
yeah, like
is subtracted from that number.
yeah. But there's a limit to this because
There is an upper end limit to this.
yeah, we can't infinitely continue to supply voltage
Right.
and continue to get more speed out of a motor. Like there's diminishing returns involved here.
Yeah, well, and also there's the other concern of that, which is, you know, at extremely high speeds, when we're talking about like if we increase the voltage too much, it will actually start arcing
Yeah, that's
to other fields from the brushes.
yeah, that is also another, like, that's a material limitation that you're going to run into.
And you'll see this if you've ever operated a drill.
Yeah,
Commonly, that's our reference for
a
this.
brushed DC
a
drill.
brushed DC drill, or a or that you will, like, if you work with one of those in the dark, you'll see that there's a lot of sparks going on inside there.
Yeah. So really roughly, I think we'll speed through these next slides here just to kind of briefly talk about this. There's a bunch of different applications for DC motors. Anything that needs lots of torque at the low end, DC motors tend to be your first choice for the most part.
Because they get maximum torque speed, like maximum torque at their lowest speed. So, so you've got all kinds of different motion control, process control. It's really nice to have that like instant startup of torque.
There are a couple of different common configurations here. You have a permanent magnet DC motor, which means that basically the field windings are magnets instead of actually coils of wire.
Yep.
There are certain advantages to them. Research them as necessary.
Yeah, so like as we go through these ones, you'll see a series motor, and you can kind of sort of absorb these on their own, and the pros and cons with relation to them. We wanted to give you kind of a cataloged view, so you can see the variety that's out there. It's not important for you to memorize all these.
You guys don't need to, like, I don't memorize this stuff, quite honestly. I go back and I look it up when I need it.
But when you're going through this the first time, it's worth looking at them and seeing why, and trying to apply this to like what we've already spoken about as to why things are wired up the way that they are, and it'll deepen your understanding of how any motor works.
Yeah. Definitely spend some time like examining like the diagrams that are on these slides and trying to interpret like how they're wired together, what that implies about the characteristics of the motor.
Yep.
But we don't expect you to have this like memorized when you come to class.
And this stuff will, like, if you're dealing with any individual motor, you're likely going to be able to see this on the data sheet for that motor.
Yeah.
As to how it's specifically applied there. The last thing that we really want to talk about here is the DC motor drives, which are essentially just voltage regulators. Because if we're controlling with a DC motor, we're just wanting to control the speed, and so that just controls the voltage that we're sending to it.
Yeah, and so higher voltage, more speed; lower voltage, less speed.
Mm-hmm.
That's what it is at the end of the day. There's some additional detail here about some more advanced types of drives. This is a diagram for how a more sophisticated DC drive would interact with a motor, but
Yeah, and in this case, like this one's significant because it's actually taking a feedback signal to make sure that it's actually like it's a
at the-
control loop to indicate
Yeah.
that it's at the actual speed.
yeah, and there are drives that use some type of encoder or motor feedback to do this.
Yeah.
But it's this same theme shows up in a bunch of different types of motor control applications.
Yeah.
So take a look at this. But I think at the end of the day, like that's essentially what DC motors
Are about.
are about. Not a whole lot.
Yeah,
to 'em.
we talk about it to kind of like bring them up. Like they're called DC motors, even though that they're actually switching current inside of them. It's what you plug them into. It's
Yeah.
the power source is why they're called that.
Yeah.
And then AC motors function on fundamentally different principles, and we'll get into those in a later video.
Yeah, we'll get into those in later.